Okay, hello everyone. I'm back. Um, in this slide, we're gonna see some more details how the electron is moving in a silicon material under under an electric field. So here, let's read out all the sentences one by one. When an electric field, for example, E dot G that indicates, for example, because of an externally applied voltage, the electric field has been formed, okay? And this formed electric field is now applied to a semiconductor such as silicon material. So mobile charged carriers such as electron or a hole, they will be accelerated. They will be forced by the electrostatic force. The force coming from what? Coming from the electric field. So where does the electric field come from? Externally applied voltage, right? So from the externally supplied electrical energy in the format of electric field, the electron in silicon material is going to be accelerated. So this E indicates the electric field from plus toward minus electrode. The electric field is formed. So now negatively charged electron is now moving toward plus electrode. But it never go straight forward. Because of what? Because of the scatterings. Okay. So as we have learned, there are three primary types of scatterings. Remember them: phonon scattering, ionized impurity scattering, and carrier-to-carrier scattering. So those three scatterings will be combined to determine how the electron is moving toward plus side. Maybe it is now first accelerated toward upward direction. Afterwards, the very first silicon um, or any type of scattering has been happened, and it is now toward plus electrode gain. However, the direction has been totally changed from south to north. Direction has been totally changed toward 7 o'clock direction, and second scattering has been happened, and third scattering, fourth scattering, fifth scattering. Those are scattering events are happened quite often, and each instant direction of electron movement is quite often changed. But in the end, the electron is moving toward the plus electron direction. Okay, so we can conclude that electrons drift in the direction opposite to the electric field. So now the charged particle is moving toward the left hand side. I'm talking about the net movement of electrons in a semiconductor has been happened because of what? Because of this electric field. Okay, so because of with the help of electric field, the electrons, the net movement of electrons have been happened by what? By drift mechanisms. So because of this drift mechanism, current can be formed and flows across the silicon material in the direction opposite to the electric field. Okay, the current is not in the same direction of the electric field, because I'm talking about the current flow. The electron itself, the electron is moving in this direction, which means the electric field is applied here in this direction. So the current is formed in the same direction of electric field. However, electron is now drifted or moved by drift mechanism in the direction opposite to the electric field. Okay. All right. Last paragraph said because of scatterings, you know, three different scatterings, electrons in semiconductor do not achieve constant acceleration. That's true, right? It would prefer to pursue a constant acceleration. That would be happened if there were no scattering. However, in real, there are tons of scattering events happened while the electron is moving, okay, in a semiconductor. So because of many scattering events, a constant acceleration cannot be achieved by electrons, okay? So to make our life easier, to more simplify the movement of electrons in silicon material, all the electrons can be viewed, can be understood as what? As quasi-classical particles, which are moving at a constant, okay, at a constant average drift velocity, such as Vd. Okay, so in the next slide, we can write down the equation to describe the momentum of electrons in silicon material. Okay, now let's take a look at the electron momentum. With every collision, so with tons of scattering events happened, in every single collision event, the electron would lose its momentum. So what is the momentum? Momentum is described as its own, mass times what? Velocity. So now this electron is, moved by electric field. In other words, this electron is moving by drift. So the velocity of this electron is described as v sub d, indicating drift velocity. Okay, some effective mass, definitely because the electron is now moving in a silicon semiconductor. So I have put the asterisk mark as superscript m sub n asterisk times v sub d drift velocity. So this physical quantity indicates the electron's momentum. So with every collision, the electron is going to lose its momentum. So original amount of momentum is described as mn asterisk times v sub d. Okay, so this amount of electron momentum is going to be lost when when it is colliding with silicon atoms or phonons or what else? Ionized impurity atoms or what else? Electrons. Okay, so with every collision by any type of scattering mechanism, the electron is going to lose its momentum, described as the physical quantity of mn asterisk times v sub d. I mean that this amount of momentum is going to be zero right at the moment of the collision is happened. Okay, now for a given electric field, a electron, another electron, those two electron, no, not those two electrons, sorry about this. Electron has now hit the silicon atom, in other words, a phonon. And now its momentum is zero. That's it? Is it all? No. Still, electric field is existing. So another force is going to be applied on this electron because it is ionized. Okay, so as we have learned, force minus q times electric field is going to be applied onto this electron, even though right at this moment of collision, its momentum is zero, but the force that it is receiving coming from the electric field is still non-zero. So it's going to be accelerated. So now let's calculate how much momentum the electron can have from the electric field is. Let's think about the units for momentum. So this unit is kilogram mass times velocity centimeter per second. Okay, and here I would like to use unit for force. So unit for force, what is it? Newton. So You may remember this equation. Force F is equal to mass times acceleration. Think about the unit of this guy, m times a, kilogram. For m, what about the a? Centimeter per second square. So you know the unit for acceleration. Acceleration means for a given time interval, how much velocity has been increased or decreased. Okay, this indicates acceleration. So in terms of unit, velocity, the unit for velocity is a centimeter per second, and time interval is second. So you can multiply them. You're going to end up with centimeter per square centimeter as the unit for acceleration. Okay, so now force. The unit for force is kilogram times centimeter per square second. But the unit for moment is a kilogram times centimeter per second. Ah, we want to match both units. What kind of thing should be multiplied? Second, right? Then it's going to be canceled out. Then we're going to end up with the unit for momentum. Same, right? So force times time indicates momentum. So what kind of time should be applied here in this situation? A single collision has been happened, and it's going to be accelerated by with the help of this electric field. But at some point, another phonon, silicon atom is here, then the electron is hit the other silicon atom. Then it needs a certain amount of time from the collision event number 1 to collision event number 2 in between. So it needs a certain amount of time to travel from collision site number 1 to collision site number 2. So this time indicates scattering time. In more detail, scattering to scattering time. Okay, but we are not talking about a single electron, but we talked about all the electrons in silicon materials. So this time is hard to define. Why is that? Because a very hot electron means an electron with high energy would be much more active. So it's going to hit more frequently. But relatively, you know, non-very active electrons, which has a lower amount of energy, would hit the silicon atoms less frequently. So it's hard to define the exact value of scattering time. So we are going to use what? Average time. Between what? Between electron scattering events. So plug in here tau sub mn. So m's scattering to n's scattering event. In between those two collision events, it needs a certain amount of time. So that average time is denoted as tau sub mn. Okay, and in front of tau sub mn, you can find out minus q times electric field E. What is this? That is force. Okay, so force times time is identical to the unit for momentum. Okay, so now let's erase all of them in this note, and now minus QE times tau sub Mn is equal to what? Mn asterisk times V sub D. Okay, now we're gonna get this equation that I have just written in the previous slide. Now with respect to the average drift velocity, then you're gonna get this equation. But previously I said if electric field intensity is increasing and increasing, then drift velocity becomes higher and higher. So we're going to intuitively expect this shape, this plot. Drift velocity is proportional to the electric field intensity. Now, from this equation, you're going to derive the coefficient between drift velocity and electric field. What is this? This is electric field. So leftover is Q times tau Mn divided by times tau sub Mn divided by Mn asterisk. This is the coefficient for what? For this relation. Vd is proportional to electric field intensity. Okay, so now this Vd is proportional to the electric field, and coefficient is defined as Q times tau sub Mn divided by Mn asterisk. That this metric or this quantity indicates mobility. Okay, so remember this quantity Q times tau sub Mn over Mn asterisk is matched to the mobility. I said mobility. Why mobility has been used to name these three terms combined together. Think about this tau sub Mn, scattering to scattering average time. If this time is very long, meaning that a collision event number one is happened, and like 1 minute later, the second collision event has been happened, which means the electron is moving quite well, right? Without any collision, it is moving well. So we can claim that its mobility, how good, the degree of movement, okay, mobility is very good because the scattering to scattering time is very long, so it is moving well, okay? So mobility is better, mobility is improved, mobility is higher when scattering to scattering time is very long. Now let's take a look at the effective mass here. If this effective mass becomes heavier and heavier, the mobility becomes lower and lower. You may intuitively understand this. With a heavy guy, it's hard to move around. Okay? With a lighter weight, you may be better move at a faster speed. Okay? So same thing can be happened in electrons in silicon material. Okay? So now let's define the mobility for electron. Mobility for electron mobility is Q times average scattering time divided by effective mass. Similarly, we may derive the whole mobility mu sub p Q times average scattering time over hole's effective mass. Okay, so whenever you have a chance to hear the mobility, always think about drift velocity and electric field, and they are proportional to each other, and the coefficient of it is mobility. Okay, again, mobility is the coefficient for the relationship between drift velocity and electric field. But again here, drift, and here electric field. Electric field is voltage difference. Okay. So for given voltage difference, or simply speaking, for a given voltage, drift can be happened. Why this drift is happened? Because electron holes are charged particles, so those carriers can be moved. By what kind of action? By what kind of action? We have learned the three primary types of carrier actions. Number one, drift. Number two, diffusion. Number three, recombination generation. So drift is always closely associated with voltage difference or electric field. So these are all things with the electric field E, they are connected through mobility. Okay. Whenever we are talking about mobility, always think about, aha, there exists a voltage difference. There exists the drift electric field. They are accelerating or deaccelerating because of what? Because of a scattering, phonon scattering, carrier to carrier scattering, ionized impurity scattering. All the topics that I have explained in chapter 3, they are connected and hooked up together. Okay? And ending Richard is described and melted into the concept of mobility. Okay? And here is a table summarizing the mobility value of electrons and holes in different materials such as silicon, germanium, gallium arsenide, indium arsenide. Take a look at the number. Electron mobility in silicon is 1400. Hole mobility in silicon material is about 500. What about the germanium? Electromobility in germanium is approximately 4,000, which is 3 times higher than the electromobility in silicon. What about gallium arsenide? 8,500, almost 5 times higher than the electromobility in silicon. That's the reason why gallium arsenide material is widely adopted in industry for what? For high-speed integrated circuit applications. Why high speed? Because the mobility of electron is very good, super good, 5 times higher than the mobility of electron in silicon. So the innovation or change of using different material is always associated with the mobilities of electron and holes. And that is associated with the operating frequency of the circuit system. Okay? So take a look at the mobility values, and if possible, please remember the mobility value of electron and holes for silicon at least 1400, 470. That's a kind of common sense if you'd like to have a job in SK Hynix or Samsung or Micron, Intel, in big IDC company. Please have those numbers in your mind. That is a kind of common sense. And here is an example regarding drift velocity calculation. So take your time to calculate the drift velocity value for holes and hole mobility. Please have please give it a try to address this question. Okay. The last concept left in this lecture note is mean free path. I guess we don't need to spend too much time here because we have already learned the concept of thermal velocity and collision, the scattering time. So average scattering time, and here thermal velocity is average uh, thermal energy that a single electron has. So average. So this is associated with the average is something. But what is this? Think about the unit for VTH and tau. That unit is centimeter per second, and times scattering time. The unit for time is second. So they are cancelled out. Leftover is a centimeter. So that is associated with average length. Average length, in other words, average distance traveled between two collisions. So that is named as a mean free path. Average length between two collision events. Mean free path. Okay? Mean free path, well, it's a very simple concept. Average velocity times average collision time. We're gonna have an average distance traveled between two events, collision events. Okay, so here are the summary. Here is a summary that we have learned in this lecture note, chapter 3, and the left about the drift. Okay, so please review all the stuff that we have learned by today, and see you in the next movie clip.